All right.
So, good afternoon, NetPulse, and welcome to a new seminar of our series. Today's speaker is Arash Badi Modiri, that is now a postdoc at Aalto University in Finland. And the title of the talk is Reticula, a temporal network and hypergraph analysis software package. So please, Arash, whenever you're ready.
Thank you. So, good morning, evening, or afternoon. I'm Arash, and today I'll be talking to you about this software library that I wrote as part of my PhD, and a little bit after that, more in general about software publishing in as part of your research. And the upsides and downsides and how to reconcile it with your usual obligations as a researcher or a PhD candidate. So, but first, let's focus on Reticula. The name comes from reticulum, which is a kind of a general purpose kind of Latin word for things that connect to each other, like a net, as in a fishing net, or as in a network. You might have heard reticule used as in this plus sign in a like a gun sight for a weapon. But the idea here is to provide a general purpose interface for working with networks. So there are software packages now for dealing with static networks, directed networks, undirected networks. There are separate software packages for hypergraphs. There are a couple of temporal network software packages. But when you think about it, there is no umbrella project that just supports networks. Can enable you to interact with different types of network, regardless of this sort of kind of implementation detail or the characteristic details with the same kind of interface. But here is a possible solution. So the short of it is that I had a lot of code working with different kinds of networks gathered up as part of my research work. I kind of put them all in one package and published them. So that's how the kind of interface goes, generally very similar to what you're probably used to from like Network X. Also a little bit maybe different. But here's the Python interface. There's also a C++ interface, which is what I mainly use for my own work. Both of these kind of use the same C++ backend. So you just import it and then create a directed network, give it a list of edges. Or you create an undirected temporal network and then give it a bunch of events or edges. So here we are saying vertices are 0 to 9, so range 10. And there are two events or two edges in this undirected temporal network. Node 1 connects to node 2 at time 3, and node 2 connects to node 4 at time 2. So you can see that kind of the two different kinds of network can share the same kind of interface while working with them. The software is also okay. So working with different kinds of networks can also has its downsides. There are things that are defined for specific types of network, but not defined for other ones. So, for example, let's say connected components. Connected component is very well defined for undirected networks, but for directed networks, it has its own ambiguity. So, do you mean weakly connected or strongly connected? So this software, this package is tries to kind of disambiguate this by kind of failing whenever you ask it to do something it's not sure. Basically, so for example, if I generate a directed network with certain edges, ask it to give me the connected components of that directed network, it's kind of gives you an error. The error is Geez, not an undirected network. I don't know how to do this. But if you ask it the right question, ask it to give you the weakly connected component, it will give you the answer. And this is a choice. This is a choice that different pieces of software made a different way. You could, for example, Network X would happily give you an answer for connected components of a directed network. It would assume that you want weakly connected component or strongly connected. Actually, I don't know. And that's the problem. The problem is that someone reading your code would not know what you intended to do by this line of code if you just use kind of some implicit assumption about this sort of typed functions. Instead, if you use functions that are not ambiguous, then someone reading your code would have a better time. Also, you can you might have noticed this brackets in front of this types. This is basically specifying what are the types of vertices in these networks. So here, for example, we're defining an undirected network where vertices are integers. Sorry, I'm a little bit sick. I might cut off at some point, but I'll be back in a couple of seconds. Okay. So here, for example, you see that there's an undirected network where vertices are integers, and we give it vertices and edges, and it will create an undirected network with integer vertices. Okay, but the package also supports kind of more complex types of vertices and edges and so on. So for example, if you do the Cartesian product of two undirected networks with integer vertices, your result would be an undirected network where each vertex is a pair of integers, right? So these types are to some extent composable. So here is another example. You're creating a directed network where each vertex is a pair of integers and strings. So you can see here vertex 1 is 1 comma hello, and the second one is 2 comma world, and each one is one vertex. So where does this idea, this notation of square brackets indicating types come from? This is actually something that is seen in other places in Python as well. So for example, this sort of generic type interface, you want to specify that this function receives. So okay, that's how people normally define functions when they don't care about other people reading their code. If you care a little bit more about people reading your code, you might specify that, oh, this function takes a list and outputs a float. But this is also a little bit ambiguous. Maybe you don't accept all sorts of lists. Maybe you only accept lists of integers. Otherwise, your function might not work. So then how would you specify that? You can specify it like this. You specify it as a list of integers for this argument. So this integer in square brackets here is a kind of generic parameter. This list is a generic type. So lists, you can have lists of anything, lists of strings, lists of integers, lists of floats. You specify lists of integers here for this function. So this is standard Python interface, a standard Python API that you can use in your code today. So yeah, so that's kind of an overview of where the square bracket interface comes from. But like in a little bit higher level, this is just a direct translation of the same idea in C++. In C++, you can also have this kind of templated types where the type is a kind of a function or templated with kind of subtypes. So here, undirected network of integers that's how it's defined. And here is how the same thing is defined in the Python version of this binding. So this binding is basically just a translation of the C++ code. We have is other places as well, like NumPy has the same kind of issue. You want to interface with a type language, you have to have type somewhere. But kind of the issue with NumPy is that it's really easy to forget that it's doing this. But it's you're specifying a type whether you know it or not. So there's a downside here. And also this type specification is not as easily composable. It's not as easy to say, oh, it's possible. It's very difficult to specify, for example, an array of pairs of things. You're probably, if you want to do that, you probably have a better time trying to come up with a two-dimensional array or two different arrays that have the same length or something like that. And also this kind of hand-wavy approach with types leads to weird situations like this. Sorry. Like here I'm defining an array of integer numbers and an array of complex numbers of the same length. And then I'm comparing them. Like, what does that mean? What does it mean to do A larger than B when one of them is a complex number? That shouldn't, that if at any point in your code this is happening, probably means that you are doing something wrong and it should let you know that you're doing something wrong. It's a bug which you should fix, right? This is not some convenience. This is a problem. It's probably rearing its head because something else went wrong in somewhere else down, like before this. So good API would fail here, would give you an error. Or you might have encountered this sort of problem with NumPy, that when you give it a bunch of things, one of them is and not exactly the same as others. Now you have an array of whatever this is. This is kind of Unicode arrays or something like that. That's probably not what you want. That's I can say that's entirely not what you want. This I would see it very unlikely as that's what a user actually likes to see. But that's what it happens anyway. It should give you an error at this point. It doesn't. And yeah, also like kind of implicit types have this sort of other kind of issues. Like here you can see it is trying to make it look as if this is doing the same as a Python integer here, right? You're not specifying any specific type of like limited size integer. So it's pretending that you can do with this NumPy array whatever you can do with a normal integer. Well, in the normal Python integer, you can calculate to the power of 100. You would just do it. It's a big int type, but not with a NumPy array. It would just give you weird results. It would happily overflow and don't even tell you about it. And it does weird stuff. Like, who can guess what the output of this code would be? Would it be 0? Would it be this number? Would it be something else? I don't know. Well, I know, but that's exactly the kind of thing that we had before that you definitely don't want. Now, instead of an array of numbers, you have an array of Python objects, which is its own kind of bag of, yeah. So yeah, you don't want to assume types. You don't want to deduce types all the time. And you don't want to do careless type coercions. So that's kind of the guide lines for basically creating any type of library that deals with different types of data. And kind of I got here through trial and error and doing the wrong thing and getting hurt and then backtracking and doing the right thing. But I'm gonna start skipping a little bit here, but what is the unifying principle behind all these different types of networks? So now we're getting back to actual topic at hand a little bit. So my kind of idea here was that a network, regardless of its type, regardless of its like this sort of microscopic properties, it's a bunch of vertices and a bunch of edges. The thing that makes different types of network different are the properties of the edges. So kind of a general view of an edge that would encompass a hyper edge or a temporal network event or a directed event or a directed link would be so one edge would have a set of mutator nodes, so a set of nodes that would cause an effect, a set of mutated nodes, the ones that can receive an effect, and the concept of adjacency. So mutated nodes are very easy to understand. So for example, for an undirected network, you say A is connected to B means that A can cause changes in B and B can cause changes to A. So A and B both are mutators and mutated. And two edges are adjacent, very simply if they share at least one node in common. What does adjacency mean in this context of cause and effect? It means that an effect transmitted by the first edge can be transmitted by the second one. So if that is true, then we say first edge and the second edge are adjacent. For temporal networks, that adjacency is slightly different. Adjacency still means the same thing, but other than having one node in common, one edge should happen before the other one. So effects can only pass through the second event if they've already passed through the first one at some earlier point in time, right? Things don't go backward in time. So if your edges provide these interfaces, there's these three kind of set of interfaces, then you only need your network to be just a bunch of one type of edge and a bunch of vertices. And with this, you can support all these different types of network with the same kind of interface. Directed, undirected networks and hyper networks or hypergraphs, then the difference would be they allow more vertices as mutated and mutators. And the same with temporal networks and temporal hypergraphs, directed, undirected, etc. With this generic interface, then this library defines various ways of generating random networks or reading and writing stuff from files or to files. For static networks, you can, for static dyadic networks, you can interoperate with network X, like load the network X static network as a native network library. And you can also do various shufflings and calculate large scale and small scale properties. But I have a couple of examples, and then this part would be over. Like this example, you'd see that we're generating a random hypergraph with a specific degree sequence, and then measuring its largest component size, right? Its largest connected component size, and plotting its connected component size distribution and shortest path distribution from node 0. So it's, again, very similar kind of general API with network X. You generate your network with a function. You can use the largest connected component function to give it the network, and we give you the largest connected component. You can calculate its size using len. Here we're getting all the connected components and plotting a histogram. Here we're getting all the shortest path lengths as a dictionary and plotting their histogram. This is the source node. So very, very easy to understand up to here. Here's another example. This is the giant component, emergence of giant component in illustrating networks. Very classic example. You can see we're generating for each value of P, for this GNP network, from 0 to some value is like 2 divided by n. We generate a random network with that P and n of 100,000, and then calculate the largest component size. It will give you the phase transition emergence of the giant component. But this uses one CPU. It's not exactly, you know, in a modern kind of computing environment, you need to use more than one CPU, because that's how computers scale nowadays. So what if we want to use more than one CPU? You can always use processor pool multiprocessing in Python, but with this library you can do also multi-threading. Multi-threading, it's much easier to spawn new threads. They use like less memory because you don't have to have completely separate Python threads loading the same library and whatever other library you're using into their own bits of memory, so they share memory with the main process. So here's an example of using this thread pool executor, which is part of Python standard library now. So this is the same function as before that generates a network, calculates its largest connected component size. And yeah, here say create 8 workers or 8 threads and calculate this function for different values of P, and then plot the same thing. So this uses 8 cores. Kind of this is the last example, a little bit more involved, is a temporal network example, kind of showing the powers of multi-threading as opposed to multiprocessing. So let's say you have a big temporal network, one large temporal network, and you want to calculate reachability from every possible node at every possible time for different values of waiting time. So what is this waiting time reachability? You have you can have a simple spreading process which starts from a node at a specific time and takes all the possible events from there, kind of grows like a tree in your network. Or you can have a limited waiting time reachability, meaning that that spreading agent won't stay in one node for more than a certain maximum delta t. If it doesn't spread in that delta t, it's going to die out. So for example, this would be more realistic if you're simulating a disease. So you want to calculate the maximum spreading of a disease, or the kind of upper bound of a disease. The disease doesn't stay in one person more than 2 weeks, so you put a maximum waiting time of 2 weeks. So again, going back to this, we want to calculate the average volume, or the average number of nodes that get sick, starting from his average on every node and every point in time as starting point. So let's say this is our network. We generated using this random network function. This has like 1 million events. And then for each different values of this waiting time, we run this function. So you can see that the network is defined outside of this function, and we're passing it here. If this was a multi-process kind of situation, this was a processor pool, then this network object had to be moved to each process when it starts, right? Because we're passing it here, right? And then you know, after we're done, then the results had to be transferred back. Then the next function call, the whole network has to be moved there, stay in that memory of that sub-process, then has to be moved back. Because this is a multi-threading situation, these function calls on different threads, they're all accessing the same temporal network object. So it's not being copied anywhere. And that kind of allows you to utilize kind of modern computing environment a little bit better. Usually you're limited by number of cores or memory divided by number of cores. Usually you have a few gigabytes of memory per core. With this approach, you can have all your cores using a shared central memory, like just the same instance of your network without kind of copying it out around everywhere. So this example, this was on my own computer. You can see that it's using all the cores, and my CPU is only using a little bit of memory. Yeah, you can kind of read more about it or just try it. You go into this website. We just recently published this is a software package, which we'll talk about a little bit more later. Yeah, that's how you can read more about it. So yeah, you can also kind of contact me if you're interested in anything. And yeah, thank you.
Thank you for the first part of the talk. So if anybody has question on this part, can unmute them himself and just ask.
I have a question.
Okay, go ahead, Sylvia.
Curiosity. Do you have any methods for like spatial networks, like some null models for spatial networks, like, I don't know, Voronoi, Apollonian, stuff like that?
No, unfortunately. I mean, it's
I'm asking
mostly
because I'm a bit
I know.
in spatial network.
I know, and this is so the way this has happened up to now has been that
Yep.
I've put in there whatever I had to work on, right?
Yeah.
So that's kind of the process, how the process usually goes,
Reasonable.
is that you accumulate code in
Yeah.
your own work, then you kind of organize them and publish them. But then after that, this is how it grows, right? So
Yep.
people come ask, okay, is there this there? Or you come up with a new research idea in a different field and say, oh, I can put that in there as well. But you can kind of use this this weird type system here to encode some of the spatial information in
Yes, for
there.
sure.
But no, unfortunately, algorithms are not, they don't expand that much in this area. But I mean, it's possible. I was thinking about some spatial related ideas a while ago, so maybe that will get in there at some point.
Yeah, because there is nothing also I think in networks, for example. So for me it was I have to write all the code by myself, which is okay.
Yeah.
Then a lot, but maybe having something more easy to, like a tool more easy to use would be nice.
Yeah, that's definitely that's how I felt when I was starting this, is that for temporal networks I have to write everything, because they either exist but are not connected to anything, right? I have to kind of adopt it, basically, like try to connect it to whatever I have, which would take more time than just writing it from scratch.
Yep.
Or yeah, so that's how you get to write your own software package. I'll be looking forward to your
Okay.
yeah.
Thanks.
I can further comment on that. Like, I think that in this case, when you write some code that you want to be general, you really have to address some general necessity, no? Maybe you are really analyzing a specific type of network, and that won't be useful for other researcher, but maybe there are stuff that are very common that maybe you don't want to write it again from zero, from scratch, no? So maybe like spreading process on network, maybe you just as you just want to see how will be the results of the spreading process on a specific network, and you have the specific network and you put the specific network in the code, and you want to see the results. So maybe the comments and question would be, it will be possible eventually to enrich the software with other function that are the common one that someone want to use to analyze a specific network.
Yeah.
Okay.
Yeah. So kind of when you have this this sort of library and you're thinking about like extending it, the kind of things that you can put in there are that there are kind of two kind of things. One is the kind of tools that would not, like, you're adding something, you're making it wider. Like, for example, if I want to add algorithms related to spatial networks, that wouldn't cause the library to be more complex. That would, but that would kind of increase its usability in other areas. So that would make it kind of go wider. But there are some things that then would make it go deeper or make it more complex. The wider ones, usually that's only a matter of having enough time. You can always add them. They're easy to take care of over time. You write the tests, you write the functions, and they would work for a long time. The kind of deeper ones are the ones that you have to be scared about. So then for those, you have to kind of define your boundaries. Okay, this software is never going to support, I don't know, this specific type of network that would make it be 10 times more complex. So then you would be able to say, no, this software is not going to support your specific use case. Go find someone else. That's for the same reason that like Network X doesn't support temporal networks, because that would be difficult for them to add in their whatever they have right now. At some point they were they sat down, they decided that, okay, this is going to be the set of systems we're going to support. But like with this architecture, adding, for example, spatial networks would be just a matter of writing that specific algorithm, not changing everything from scratch. But yeah, that's.
So thank you. If there are no other questions on this part, I think you can go on with the second part.
Yeah, so kind of oops, what's happening here? All right. So I want to kind of talk a little bit about just everyday life of a PhD candidate doing software as part of the thing. So yeah, so as I kind of alluded to a little bit before, when I started my PhD a while ago, I started writing normal research papers on various topics around temporal networks and reachability and so on, and I accumulated code as part of it. At some point, there was enough of the code that I decided to kind of go for a software paper. But kind of there are challenges and open questions about this approach. So kind of I'm going to go through them in a QA kind of format to see how I would answer some of these challenges, or how have I found answers for these. So yeah, so one of the primary questions is that, okay, so let's say I want to do this research software thing. How much should I invest in it? How much do I need to invest in it? Would that become a problem later on? Sorry. The answer is you can put different amounts of time in it, and it depends on how much you're willing to put in it. So what I would consider to be the minimum acceptable level, if you're publishing a computational paper, is that at the very least, for the purposes of reproduction, you have to put all your code like just in a zip or something like that in Zenodo. I don't know what they call it, a package. I don't know, Zenodo thing, which is you just put all the code required for someone else to reproduce your research, along with any data that you can legally put in there. Just upload it there, give a citation to this in your paper, and then forget about it. That's a very minimum that I would consider to be, is my opinion, should be required of people publishing computational software, computational papers. It's not required, but it's very much encouraged nowadays. Especially if your data is publicly available, then doing this becomes more important. This would allow other people to kind of have an easier time getting into your line of research and maybe build upon it. But kind of the next level is to, if you're creating a new algorithm, coming up with a new idea, a new way of representing something, is to create a reference implementation. So reference implementation, you really want to, it's optimized for other people reading your code. It's not optimized for being fast or being general or anything like that. And you're basically writing code for long-term use. So you're writing code that is supposed to be usable 20 years on, but doesn't need to be fast 20 years on. It needs to be informative to whoever's looking at your code. So you want to use as few dependencies as possible, right? I'll have examples of all of these later on. And you don't need to update it constantly, but it's good idea to have it work at least with the minimum, like with the most recent version of the programming language that you're using. So I don't know, if you write it with Python 2, or you wrote it with Python 2 20 years ago and Python 2 is being deprecated, then go change it to Python 3. That happens every 10 years or so, but it's a good idea. Kind of the next level of commitment would be to publish a library or an open source package or something like that. That's optimized for people actually using it. That would be things like NumPy, Network X, Reticula. You're optimizing for other people's experience, and you have to keep it updated, but you have limited responsibility to what other people need. Like if there is a bug, it's a good idea to solve the bug, come up with a new version, but you haven't promised to anyone that you're going to do that. You can do it on your own time, but you have a general spirit of obligation to solving these bugs that people report and so on. So it needs some constant effort, but you can do it as part of, as a kind of side project, not your main thing. The next level here would be to just make a product out of it. You can actually make money out of it if you go about it correctly, but then that would become your job, right? Then you have to, you're contractually obligated to support whatever business is using your code because they're giving you money. So here's an example of just putting your code in a Zenodo thing. And this is like one of my papers a couple of years ago, actually published 2022, but for 2 years ago. And yeah, so in the paper, there's a reference 84, which is source code for this paper available at this URL. And this Zenodo is designed so that it would be available. This link would be available for in long term. You don't have to worry about, I don't know, 20 years in the future, GitHub going out of business, or I don't know, something like that, like something like what happened to SourceForge or a lot of other places. So yeah, I would say if you have code for a paper, the minimum you can do, make everyone happy, is to do this. Put it there, let other people have a look at your code. Nobody's gonna, inspect it with too much detail, but that one poor person that wants to find, some detail about how you implemented this function, they would save them 2 weeks to be able to go and just download your code and just see how you use this one thing. The next level is the reference implementation. for example, this paper provides a reference implementation. It's a, again, like this is, it's not fast. It says it's a pure Python library implementation. It's not efficient, but it gets the job done. Other people that implement these algorithms presented in this paper can compare the results with this reference implementation. It's easy to read, and kind of makes some stuff that is in this paper but not clearly explained more concrete, because in the code everything has to be taken care of. Like you would see that, okay, how does this code deal with negative times, or how does it do with unsorted events or things like that? They might not have mentioned these in the paper. You might not have mentioned exactly how this works in your algorithm paper or your method paper, but you have to have, at least done a little bit of work on them in your reference implementation. So it gives a more concrete version of your paper, basically. But yeah, and you would have to keep it working, but you don't have to make sure it's always optimal or efficient or things like that. Sorry. The next level would be to kind of package your software in its own library, as its own library. And that's kind of, for an example would be this Reticula that I was talking about in the first part. This packaged as its own library and now published as its own paper. This would need kind of more commitment. You have to keep it updated all the time. For example, Python creates they release a new version every year on October. So at least once a year, I have to go and compile this with a new Python version. At the very least, if there's a bug, I have to fix it because other people might be relying on it. At the very least, I'm going to be relying on it. So, yeah. And then the next level would be to kind of come up with a more of a solution for other people's problems, and then market it as such. Like, for example, Raftery is a kind of in the same lines as temporal networks, kind of general purpose library or solution. They have business clients. They have to give support to those business clients. But the upside is that they also get money from those clients. But what's in it for us as scientists for now? Now I'm going to focus on just the reference implementation and library, because the kind of reproduction and the product are kind of outside of this area for now. The reference implementation, it gives people a better chance of being able to continue what you did, or cite you, or kind of makes your research area more appealing to other people, which sometimes you would need. Sometimes you're working on a research area with not a lot of people work in that specific niche. You want more people to become interested, but not everyone is willing to sit down and write all the code from scratch. So that would make it slightly easier for everyone else to kind of continue on where you started. And kind of library, or open source library, kind of goes next level. It allows people to just directly cite your work. Yeah, so okay, so let's say you have one of these and want to publish it. So I would say reference implementation, publish it as part of the paper that it's implementing. It's not necessarily a good idea to publish it as a separate piece of work, and it definitely improves the odds of you going through the referee process, a peer review process, with a better outcome. I've seen that multiple times, that referees usually like it very much when they see that you put the extra effort in there to provide an implementation that other people can really easily get into and just read the code if they don't want to read your details of your algorithm in your paper. It makes it much easier for them to look at what you've done, and makes it much easier for them to kind of give the thumbs up to your works of research. And for a library, you can publish it as a software paper. You can publish it, for example, there are journals specifically publishing software paper. For example, Software X or Siam Scientific Computing, or there's the Journal of Open Source Software, which is kind of more works more on the principles of open source. Like you can go and volunteer for reviews of other people's, and yeah, very kind of modern sort of collaborative journal. Or you can also try publishing it on normal scientific venues where you publish. A lot of these places, like Physical Review and so on, would allow publishing software, but specific software venues a lot of the times provide a better environment for publishing software. Okay, so let's say you want to publish your library. You have a separate library, it's not a reference implementation. You have a library, you want to publish it. What do you need? Well, a lot of places require you to have an open source license for your software. You can't really publish a closed source software in these journals. Probably you can publish it somewhere. They require you to show that this is a library that somebody needs. That somebody can be you, but you have to have examples of paper or papers where this software or some previous incarnation of this software was useful. So in my case, when I published Reticula, I could show previous papers on my PhD that this previous incarnations of this library was used to kind of show or create the results. They also, some of them need you to have some level of documentation and some automated testing, or testing, not necessarily automated. But they instruct the referees to actually look for documentation and testing as a minimum, which is a good thing. It helps you in the long run to keep track of your own project. You need some testing, and you would need a good deal of documentation if you want people to actually use your code successfully. And you have to provide one method of communication, like a place for people to ask questions or write bug reports, an email or a GitHub issues page or something like that. Yeah, but what about unofficially? So you would need to present the journal with many people that would be potential referees for your paper. A lot of these places have problem finding people that would do peer reviews, because each paper is kind of it's in one part of science. No, I can't really review a paper about ad hoc wireless networks. It's not my area. Although I have done some software work, that doesn't make me qualified to do review of a software for that specific area. So you would need to come up with a lot of people that might be able to do peer review of your paper. Otherwise, you would have to wait for a long time. And people are going to be confused. The referees are going to be confused because it's not very common that you would get a referee request for a software paper. So they might ask that, okay, you've shown the software, now where is the science? And then you have to be ready to explain that, no, this is a software paper. Here's the guidelines for this journal. So yeah, here are the other papers that use this software to do actual, hypothesis testing or other sort of normal science. So yeah, okay, a lot of you are doing PhDs or will be doing PhDs. So I used the software paper in my thesis. You might also be able to use the software paper on your thesis, which is nice because some universities or some countries require a minimum number of publications for you to be able to graduate. That kind of helps you. You've worked on this, so now you'll be able to claim it as part of your kind of maturity as a independent researcher. But in general, why bother? Well, it's good for your thesis, and it's good for your immortal soul. Like other people are gonna use it. It's gonna make them happy. It's gonna make their life easier, and they're gonna appreciate it. It's gonna be a good deed that you've done. But you can use it in your thesis, or you can present the work on its own in conferences, as I'm doing right now. In other presentation venues, you can and you can easily cite it in your future work if you use your own software. It's better than citing a work that might not be directly related. It's very clear that you're citing it because it's a software you used. And yeah, it's very good to have a kind of a more multifaceted kind of CV for yourself. People, especially in nowadays in academia, are starting to pay more attention to this sort of, the same as like having a good GitHub profile. If you have an active open source software library, that's a very good sign that you know what you're doing when it comes to computation, right? It's a good sign. And if you want to go outside academia, then that becomes even more important, right? Because you can't really, your number of papers and citations wouldn't carry you as far outside academia. But an open source library, that's the language that like a software company or a data analysis company would understand more readily. So that kind of gives you a boost in the job market if you want to go outside academia. Yeah, so that's kind of my brief kind of overview. But yeah, if you have any questions or discussions.
Yeah, thank you. Yeah, if anybody has some question, can again unmute them himself and ask. Okay, maybe I can start because I have a lot of questions actually. Because I'm in the situation now where I have where I submitted the paper and I have some code for it, and I think it may be very useful for the general public. Well, for science above all. But I'm not very good at programming or writing a good program for that to be shareable and that people can understand my code. So have you any suggestion on how I can learn how to write and explain better my code? Because maybe I've done research on this topic for a year, no? So maybe to me something may looks obvious, but people won't understand that because they haven't studied on that for 1 year. So
yeah. So I mean, of course, if you want to kind of work on your skills as a research software engineer or as a researcher with like a better ability at writing shareable code, for example, there's I can recommend this code refinery courses. This is actually very useful, very nice place and a nice group of people. They have kind of online workshops that would definitely kind of give a boost to anyone that is interested in kind of writing better code as academics or using kind of getting better at using these adjacent skills like Git or kind of computational clusters, using computational clusters, that sort of stuff. Yeah, they do online workshops and stuff. I think one of the main cores of this is based out of Aalto University in Finland, but they are all over at least the Nordic countries. But okay, so but another issue might be, again, just how much time do you want to put on it in the long run, like after the paper is done with. So if that's not a lot, I would recommend share your code as a you know, Zenodo, I don't know what they call it. They call it a repository, I think. Yeah, so basically just put it in a zip directory, upload it there. It's way better than nothing. But if you're willing to, if it's something that you want to work on for a few years, or for your PhD, or for like a 2-year postdoc, 3-year postdoc, or something like that, or you see yourself as continuing on the same subject, think about like a long-term kind of package. It might be a good idea. Yeah, but don't, you don't have to choose. You can share what you have for your current paper as a, put it on Zenodo and cite it in your own paper, and then turn it also into a package later on if you decide it. It definitely helps. I've seen it in peer reviews that they would look more favorably on your paper in terms of reproducibility if you show them that it's good. I have you can have all my code. There's nothing up my sleeves, right? And it's generally a good practice for everyone. Even if you're, I know that like this is a problem with, like, you know, you people, including me, always feel like, okay, my code is not good enough. That's not the point. It probably is good enough. It is probably way better than you think it is. But even apart from that, something is better than nothing in there. So I would say share your code in your paper, but long term think about maybe a library or something. Yeah, even like a tiny library.
Yeah, that's true. I mean, it's or I don't think my code is good enough, or I don't know how much time I can invest on it. But definitely I think it worth the effort.
Yeah, I would say even if you don't want invest any time, just put it in Zenodo and cite it in your own paper. That's much better than nothing. Even if you think, okay, nobody's gonna read it and say, ha ha ha, their code is horrible. No, that's not you never do that. Nobody else is gonna do that to you. Right? Everyone understand that, okay, like sometimes people code in a hurry, or a project is like done by a lot of different people that kind of have different styles, so might not be consistent style. Not a lot of PhD candidates get a time to just rewrite their code from scratch because it's not clean. Like you sometimes have to do things in a hurry, or like write tests for it or things like that. These are like, we don't often get those chances, so nobody's going to judge your code for it. So yeah, share it, don't worry.
Thank you. So I think Guillermo has a question, or
yes, can you hear me?
yes, very well.
Yes, oh, perfect, great. All right. Yeah, no, thanks for the talk. It was interesting also to see the personal side and what it takes, and yeah, I was wondering because in the end it's a bit tricky because when you get it to a library, a package, it's hard to really get it through the community unless it reaches some momentum and other people gets involved, and also it requires a lot of time to get everything ready and to build the community that requires definitely like even a whole job or a grant or something. A lot of resources in general. So it's a bit tricky. I mean, I guess, yeah, if you are going to use, I mean, if it's for your personal use, and then on the same line, anyone can use it. But it gets, I guess, a bit in between sometimes. I was wondering also, like, would it be, for instance, if you create a big contribution to an existing package, existing library, but you do like a very substantial addition of some part, could that, for instance, be able to be published or something like that? Or
Yeah, yeah.
just
So
as one thing as an alternative of if to have it inside another project and then it's be more.
yeah, so the second question is kind of easy to answer. Yes, major updates to software can be published. It is software X has a specific category for software updates. But it has to be major update. Like you have to add something major. Then with the existing authors of the package and you publish a software updates paper. And then you can kind of cite that. But for the first question, I would say treat the library and its accompanying paper as with any other research work. Like when you publish a piece of research, you might get traction, you might not get traction, you might get a lot of citation, you might not. What you can do to help it is to, like any other work of research, go here and there, present it. There's going to be people having the same problems as you, right? There's going to be a few of them. You never know. Exactly the same as like any other research paper, you can kind of convince them that, yeah, you might, if you use this approach or this software, you might be able to get a better result, and they would try that and maybe become users, maybe they would not. But the kind of most useful thing for a software package, the most faithful user should be you, right? It's probably a good idea to build something that you want to use. Otherwise, it's gonna be you're not gonna have a driver. You're not gonna, if you don't need anything from that package, then even if you're not using it, then that's gonna be a hard sell for other people. So yeah, build something that you would need anyway, and then that kind of, you can write off a lot of the costs as your ongoing work of research. Then kind of market it as with any other work of research in conferences and venues like here, like where people might need that sort of software in their lives. Yeah. And yeah, so kind of community, that's a little bit more difficult than users, but that kind of comes down to how good you are in turning people. For example, I guess it was Sylvia, right? I don't know if I was asking about yeah. So if I was a good kind of community person, I would be kind of now encouraging her to write down these codes and submit it to. I'm very bad at this, so but yeah, so that's how things get started, especially like if this was like a pure Python package or something like that. It would be much easier for people to get started. Then you would more easily be able to convince them to, oh yeah, that's interesting. Can you send me an example of this? Then kind of coax them slowly into kind of sending a pull request. But yeah, that's how I imagine it goes with the community, but I'm not a very community-oriented person, so yeah. Thank you.
Great, thanks for the answer.
So any other question?
I have a very fast question, which is, have you started writing Reticula with Python or C++?
So I did what they call a minimum viable product, or what is it? A prototype, let's say, with Python, just to see if things work.
Okay.
So that took like, I don't know, that took like a week, a long time ago. I just wanted to kind of see how things would work. But from the beginning, I know that, okay, I'm going to go in this from C++ angle, because I would need the type of research I was doing. I had to use kind of high performance computing for large data sets and
Yeah.
that sort of thing. So, but yeah, but
If-
you don't have to go there if you don't
Yeah, I
want
know,
to.
but for some spatial networks, it's similar. So you have to work with very large data sets. You need to optimize memory and performance and everything.
Yeah,
So maybe, yeah, the suggestion is to try to work with C++ or even C, I don't know, something very low level, and then translate to Python language. for
yeah,
example.
like you create a binding the same way that I did. Like, yeah, write your functions in C++. Probably C++ would work better for this binding. Then you make a binding with one of these, like this PyBind 11
Yep.
or this sort of things that allow you to call the C++ functions from inside your code. Yeah, but that has its own kind of negative side effects for a library, right? It makes it harder for people to read your code, makes harder for them to kind of come up with new stuff. And of course, writing C++ is inherently more time consuming than writing just Python code. That's the whole idea of like a higher level language, is that it's
Yep.
easier to kind of write some Python code that works. But yeah, writing a C++ code that doesn't give you a segmentation fault, that's some effort, minimum level. Yeah. But yeah, I really recommend that everyone to get kind of involved in the if you have a code, share it. That's kind of my hope would be my takeaway lesson from.
It is. I think it is. So I think we can close the session. We are always looking for speakers. So if anyone in the audience wants to give a talk, just write to us. And we thank again Harash. Thank you very much.
Thank you.
It was very nice. So goodbye.
Bye, everyone.
Bye bye.
Bye.